Hello everyone, this is Professor Roman. Let us continue the ring theory lectures. We've been talking about maximal ideals. Rings that have a unique maximal ideal have some rather interesting properties, such as the fact that the sum of two non-units is always a non-unit. And also, for all elements A in the ring, either A or 1 minus A is a unit. So for simplicity in our discussion, we're going to assume that all rings are commutative. A commutative ring R that has a unique maximal ideal M is called a local ring. And for convenience, we're going to make the following definition. The non-unit set of a ring R is the set of all elements that are not units. So I'll use this notation. This is not standard, but it's useful, and it does no harm, so we'll use it. Now suppose that R is a local ring with unique maximal ideal M. Then every non-unit X in the ring generates a proper principal ideal. And that has to be contained in some maximal ideal, but there's only one maximal ideal, so that must be contained in M. Therefore, the non-unit element X is in M. In other words, every non-unit belongs to the unique maximal ideal. So the non-units of R belong to M, which of course belongs to the non-units of R because this is a proper ideal, so it cannot contain any units. And so, in fact, the unique maximal ideal in a local ring is the set of non-units of the ring. But the converse is also true. Suppose that R is a commutative ring for which the non-units is an ideal. Then the non-units of R is a maximal ideal because any strictly larger proper ideal would contain a unit and wouldn't be proper, so there's a contradiction there. And so all ideals of R are not only contained in the non-units of R, but the set of non-units is a maximal ideal, so it is the unique maximal ideal, and R is a local ring. So here's the theorem. A non-zero commutative ring R is a local ring if and only if the non-unit set of R is an ideal, in which case it is the unique maximal ideal of R. Some quick examples. All fields are local rings. Let P be a prime and let R be Z sub P to the N. N is obviously a positive integer. Then X in R is a unit if and only if it is not divisible by P. It has to be relatively prime to P. So it's not divisible by to P to the N. So it's not divisible by P, and so the non-units of this ring are the set of all multiples of P, divisible by P. And this set is an ideal, which I'll let you show. And so the previous theorem shows that R is a local ring. So ZPN is a local ring. The set, we'll let G naught, remember we've talked about these before, G naught is the ring of germs of continuous functions at 0. The units of G naught are the germs, square bracket x, for which f of 0 is different from 0. because these functions are continuous, if f of 0 is different from 0, then it's also non-zero, and in fact of the same sign, somewhere in a neighborhood of 0, and we can define an inverse. Okay. So the non-units of G naught are the germs square bracket f, for which f of 0 is 0. And I'm going to leave it to you to show that that is an ideal, and so G naught is a local ring. If Q sub OD is the set of all rational numbers with odd denominator, so it looks like this, then this is also a local ring, and I'm going to leave that for you to check. So we've got 4 examples of important local rings. Here's a characterization of local rings in terms of the behavior of non-units. Let R be a non-zero commutative ring. The following are equivalent. R is a local ring. The non-unit set, non-units of R, is an ideal of R. Non-units of R is closed under addition. In other words, the sum of 2 non-units is a non-unit. And for all elements A and R, at least one of A or 1 minus A is a unit. Now we've seen that 1 and 2 are equivalent. We just got through with that. If 2 holds, the set of non-units is an ideal, then of course ideals are closed under addition. They're additive subgroups, and so 3 will hold. If 3 holds, and we take an element A in R, then since the non-units form a proper set of the ring and are closed under addition, it cannot contain, this non-units of R cannot contain both A and 1 minus A, because if it's closed under addition, then it would contain their sum, which is 1, and it wouldn't be proper. So one of either A or 1 minus A, or perhaps both, have to be units, and 4 holds. Finally, now suppose that 4 holds. At least for every element A and R, either A or 1 minus A is a unit. If M is a maximal ideal of R, and X is a non-unit that does not belong to M, then this ideal generated by M and X, which is being strictly larger than M, has to be all of R, which means we can write 1 equals M plus little rx for some little r in R and some M in the ideal M. Okay, so I don't need that. I'll get rid of that. Okay. But XR is in I, that's M, and it's a non-unit. And so we know that 1 minus Rx, which is little m, has to be a unit, but that contradicts the fact that little m is in the maximal ideal M. No units in there. So the ideal M is actually the set of non-units. There cannot be a non-unit X outside of M. And that's 2. The non-units form an ideal. 2 and 1 are equivalent, if you remember. So we have our complete circle. Let us next, actually, explore conditions under which the quotient ring R mod I is an integral domain. So suppose that R is a commutative ring and that I is an ideal of R. the quotient ring R mod I is an integral domain if and only if it has no zero divisors. In other words, if and only if the product of two cosets, elements of the quotient ring, equals 0 implies that one or the other of those cosets is 0. That's equivalent to saying the product AB in I implies that either A is in I or B is in I. And that property has a name. A proper ideal P in a commutative ring R is prime if A, B, and P implies either A is in P or B is in P. The set of all prime ideals of R is called the prime spectrum, or simply just the spectrum of R. And let me reiterate that by definition, prime ideals must be proper. The entire ring has this property. If a product of two elements is in the ring, one of the factors must be. In fact, both factors must be. Nevertheless, it's not a prime ideal because it's not proper. Note also that that in a commutative ring R, R is itself an integral domain if and only if the zero ideal is prime. Theorem, let R be a commutative ring. The quotient ring is an integral domain if and only if I is a prime ideal. Every maximal ideal is prime. We've already taken care of part 1. Part 2 has a very simple and elegant proof. If M is a maximal ideal in R, then R mod M is a field, and therefore also an integral domain, and so M is prime. Actually, the primeness of ideals is a direct generalization of the primeness property of integers. Specifically, if P is, specifically by definition, an integer P greater than 1 is prime if whenever P divides a product, it must divide one of the factors. That's not probably the definition that you hear often. People say a positive integer is prime if it has no factors other than 1 in itself. That, in fact, is the definition of irreducible. In ring theory, there's a difference between irreducible elements and prime elements, and this is the actual definition of prime for integers, speaking ring theoretically. The two concepts are equivalent for the integers, irreducibility and primeness, so it's not the end of the world when these two terms are confused. In terms of ideals in the ring of integers, this is equivalent to saying that a product is in the principal ideal generated by P implies that one of the factors is in that principal ideal. So P is a prime integer if and only if P is positive and this ideal is a prime ideal. Now we have to add this because -2, for example, prime numbers are by definition positive, and in fact greater than 1. And so we need to, actually I probably should say P is greater than 1. Okay, that's better. Okay. Examples. In the ring of Gaussian integers, which is this ring, the ideal generated by 1 plus I is prime. And the reason is as follows. If a product of two Gaussian integers is in this ideal, in other words, if there exist integers x and y for which this product is a multiple x plus yi of 1 plus I, Then taking norms gives us a squared plus b squared times c squared plus d squared equals 2 times x squared plus y squared. Which means that a squared plus b squared we can assume is even. One of these two at least has to be even, so we'll assume it's a squared plus b squared. And it follows then that a squared and b squared have the same parity, and therefore so do a and b. And that implies that both a plus b and a minus b are even. So we can write a plus b as 2n, a minus b is 2m, and so a is n plus m, b is n minus m, and a plus bi is the quantity, is the Gaussian integer m minus im times 1 plus I. In other words, it's a multiple of 1 plus I, and therefore belongs to the ideal. So one of these factors has to be even, and that puts the corresponding Gaussian integer in the ideal. So the ideal I is prime. Here's an example of a prime ideal that is not maximal. R is z squared bracket x, the ring of integer polynomials, and I is the ideal generated by x. Then p of x times q of x in I implies that p of x times q of x is some polynomial multiple of x. And that means one of the factors, p of x or q of x, has to have zero constant term, and therefore a multiple of x, it belongs to the ideal I. So I is prime. But this ideal is properly contained in the proper ideal generated by 2 and x, and so the ideal generated by x cannot be maximal, is not maximal. Here are some additional properties of prime ideals, and I'm leaving the proof as a good exercise in practice with prime ideals. R is a commutative ring. An ideal P of R is prime if and only if, for all ideals I and j, the product ij contained in P implies one of the factors is contained in P. So this looks just like the definition of prime, but for ideals instead of elements. And that can be generalized to the product of n ideals. Also, if P is a prime ideal and I1 through In are ideals, if the intersection of the ideals is contained in P, then one of the ideals must be contained in P. And if the intersection of the ideals is equal to P, then one of the ideals must be equal to P. Finally, I should put it, okay, part 3, if P is a prime ideal and A is an element of R, has the property that some positive power of A belongs to P, then A also belongs to P. So if A squared is in P, so is A. If A cubed is in P, so is A, and so on. In particular, every nilpotent element of R belongs to every prime ideal. Nilpotent element, if A is nilpotent, A to the n is 0. That's in every prime ideal. Therefore, A is in every prime ideal. We discussed the existence of maximal ideals, and we talked about separating ideals. And that same concept of separating ideals can show that prime ideals exist. but we need to restrict attention to a special type of set X, not just multiplicative. Oh, I'm sorry, not just arbitrary, but multiplicative. And this is the definition. A subset X of a ring R is a multiplicative set if 1 is in X and X is closed under multiplication. Just a word of caution here. It's tempting to think of a multiplicative set as just a set closed under multiplication. That would seem to make sense. But by definition, there's an additional requirement, that is 1 is in the set X. In fact, the set containing just 1 is a multiplicative set. Now, if let R be a commutative ring. If X is a multiplicative set that is disjoint from a proper ideal, I, then this family, this is all the ideals that contain I and are disjoint from X, the separating ideals, has a maximal ideal M. This we know. But M is also prime, because if AB is in M, but neither A nor B is in M, then the ideal generated by M and A has to meet X, and the ideal generated by M and B has to meet X, non-trivially. So there are elements, X is in X, M's in M, R's in the ring, for which X1 equals M plus R1A, M1 plus R1A, X2 equals M2 plus R1B. Well, since X is multiplicative, we stare at these and we realize we better multiply them together. X1, X2, this belongs to X. And when you write it out, you see every one of these terms belongs to M, because AB is in M. But X and M are disjoint. So that's a contradiction. It tells us that one of A or B actually has to be in M, and so M is prime. So here's the theorem, existence of prime ideals. Let R be a commutative ring, let I be an ideal. Actually, it has to be a proper ideal. And let X be a multiplicative set that is disjoint from I. Don't really need to say proper if you're going to say there's a set, a multiplicative set that's disjoint from I, but I'll change that anyway. Then any maximal separating ideal that separates I from X is a prime ideal. So the existence of a maximal separating ideal in this family, the separating ideals, has actually served us two very important purposes. It gave us both maximal ideals when we take X equals the singleton set 1, and prime ideals when X is any multiplicative set. Now, the concept of a radical plays an important role in more advanced ring theory. So we can't go very deeply into this concept. It relates, we're going to relate it to both maximal and prime ideals, which is why I'm discussing it at all. But we can introduce the concepts and kind of scratch the surface just a little bit. And if you continue in your studies of ring theory, you will encounter radicals, and this may be of some help. The term radical is a very general concept, and there are different ways to define it, and it gets quite complicated, frankly. But here's a simple definition. If C is some class of ideals in a ring R, such as the class of all maximal ideals or the class of all prime ideals, then the radical of the class C is the intersection of all the ideals in the class. So that's a pretty simple concept. Here are the two arguably most important radicals, although I'm not sure you get too much argument, maybe from a ring theorist. Let R be a commutative ring. The nil radical of R, which we denote by script n of R, and that's not standard terminology or notation, is the radical for the class of prime ideals. In other words, it's the intersection of all prime ideals. The Jacobson radical of R, which we denote by script j of R, is the radical for the class of all maximal ideals. So it is the intersection of all maximal ideals. You might be wondering, shouldn't this be two words, nil radical? And I don't know. It seems to be one word in almost all the literature I've seen, although many authors, ring theorists included, will sometimes refer to nil radical in two words, but then later on they'll talk about the nil radical. So there's, I guess, a subtle grammatical difference that I don't appreciate. So I find this annoying, but that's what it is. Okay. And certainly not serious. Of course, since every maximal ideal is prime, the intersection of the prime ideals is contained in the intersection of the maximal ideals. Okay. Because this is, the Jacobson radical is an intersection of some prime ideals. So let's look at the nil radical first. And so n of R is the intersection of all p such that p is a prime ideal of R. We've seen that a nilpotent element of R belongs to every prime ideal. So every nilpotent element belongs to the nil radical. So for convenience, let's denote the set of nilpotent elements of ring by nil of R. So nil of R is contained in the nil radical. But the reverse inclusion also holds. If an element A is not nilpotent, if it's not in here, then this set of powers, non-negative powers of A, is multiplicative. It does not contain 0. And so the earlier theorem implies that the separating family contains a prime ideal. So it's a prime ideal that is disjoint from X. Contains 0, but all ideals do. But it's a prime ideal that's disjoint from X. And so in particular, little a to the 1, is not in the prime ideal P, so A is not in the nil radical, which is the intersection of all the prime ideals. So if an element is not in here, then it's not in here. So we get the reverse inclusion. Everything in the nil radical is nilpotent. If R is a commutative ring, then the nil radical of R is precisely the set of all nilpotent elements in the ring. So that's a very nice characterization. If you want to know if an element's in the nil radical, you just take powers. And, well, theoretically, you have to determine whether some positive power is 0 or not. One more fact about the nil radical. If we factor a commutative ring R by its nil radical, which I'll just call n, the quotient has no nilpotent elements. And here's the proof, and I encourage you to construct that yourself without looking here. hence, the nil radical of the quotient is trivial. Because the quotient has no nilpotent elements, the nil radical is the set of nilpotent elements. Okay. So trivial meaning it's just zero, contains the zero element. Okay. So in symbols, the nil radical of R mod the nil radical of R is the set containing n. That's the zero set in R mod n. So by factoring out by the nil radical of R, we factor out all the non-trivial nilpotents. Okay, let's take a look at the Jacobson radical. This is named after the famous algebraist Nathan Jacobson, who I also met in the late 60s, along with Kaplansky and some other famous ring theorists. I was an undergraduate at UCLA at the time, and UCLA had every year they had a special programs, and they picked a specialty that was ring theory. So there were a whole flood of ring theorists came to UCLA to visit, and I met several of them, although at that time I really wasn't plugged in that much to ring theory. There's a story behind this, but I won't bore you with the details unless, of course, you're interested. Anyway, it is perhaps a surprise that there's a simple characterization of the elements of the Jacobson radical, because it's a rather complicated radical, actually. If A is in the Jacobson radical, then it's in every maximal ideal. And therefore, so is every multiple of A. And so 1 minus RA cannot be in any maximal ideals, because RA is in all the maximal ideals, and 1 is not in any maximal ideal. So 1 minus RA has to be a unit. If A is in the Jacobson radical of R, then 1 minus RA is a unit. True for all elements R in the ring. But the converse is also true. If 1 minus RA is a unit for all little r in the ring, but A failed to be in some maximal ideal of M, then this ideal, we've been doing this a lot, the ideal generated by M and the element A is bigger than the maximal ideal, so it must be all of R. So there's a little r in R and a little m in M, for which 1 equals RA plus M, and therefore M, which is 1 minus RA, is a unit, and that's a contradiction. There are no units in a maximal ideal. So, theorem, let R be a commutative ring with Jacobson radical J of R, then A is in J of R if and only if 1 minus RA is a unit for every little r in the ring. And I mentioned before that the nil radical is contained in the Jacobson radical, so I want to make that a formal theorem here. Okay. We're almost done with our study of radicals. This may seem rather abstract, and it is, but you're getting a good flavor of what ring theory is like. After this discussion, we'll go back to more concrete stuff, actually. Stuff that looks more familiar, some of the common themes in abstract algebra. Okay, so we've seen that factoring a commutative ring R by the nil radical produces a factor ring with trivial nil radical. And it works the same way with the Jacobson radical. So let's let J be the Jacobson radical of R. Then the Jacobson radical of R mod J is trivial. It consists only of the zero coset. Now to prove this, we could use the definition of Jacobson radical as the intersection of all maximal ideals in J mod R, in R mod J. Then the correspondence theorem, which we haven't yet discussed, it's coming in the excuse me, in the next chapter, tells us that the maximal ideals of R mod J have the form M mod J, where M is a maximal ideal of R. Works the same way as it does it for groups and for vector spaces. Therefore, the Jacobson radical of R mod J is the intersection of all the quotients M mod J, where M is a maximal ideal in R. And that's equal to the intersection of the maximal ideals mod J, which is J mod J, which is trivial. But we haven't yet discussed the correspondence theorem, so I can't let it stand like this. Here's another proof that's, well, somewhat less elegant, but still works. Suppose that, so we want to show that the Jacobson radical of R mod J is trivial. So suppose that x plus j is in that Jacobson radical. We need to show that x belongs to j. Theorem 242 that we just discussed tells us that for every element R, we have 1 minus R times the element. So let me read that again. This is the 1 coset. It's the element 1 in R mod J. This is an arbitrary element of R mod J, and this is our x plus j. That is a unit, okay, for any R. Here's the theorem, and so we're dealing with this expression, but 1, R, and A, they're all cosets because we're in a quotient ring. And when we simplify this, it looks like that. So there's an element y in R for which this coset times the coset y plus j is the identity coset. And again, this can be simplified, and it looks like y times the quantity 1 minus rx minus 1 belongs to j, and I'm going to call this z. So z belongs to j, it is therefore a non-unit, and so 1 minus z is a unit, and so y times 1 minus rx is a unit, and since r is commutative, each of the factors must be a unit. In particular, 1 minus rx is a unit for all r, and so x is in j, and so x plus j is equal to j, and we've shown that the Jacobson radical of R mod j is trivial. And here's the theorem. Finally, to conclude, we'll discuss a connection between the Jacobson radical of a ring and the property of being strongly associate. Just to review, we say that in an arbitrary commutative ring, two elements are mutual divisors if each divides the other, and they're associates or unit related if each is a unit multiple of the other. And we've discussed the fact that associates are mutual divisors, but the converse is false in general. And in fact, the question of exactly which commutative rings have the property that mutual divisors are associates In other words, the question of which commutative rings are strongly associate is still a subject of current research. Now, we have seen that integral domains are strongly associate. And the usual argument goes as follows. If A divides B and B divides A, then B is a multiple alpha A, and A is beta B. And so B times the quantity 1 minus alpha beta is 0. So if R is an integral domain, then since B is not 0, alpha beta is equal to 1, so alpha is a unit, so A and B are associates. What can we say if R is not an integral domain? Well, if 1 minus alpha beta is in the Jacobson radical of R, then we have a theorem that tells us that alpha beta must be a unit. It's 1 minus R, 1 minus alpha beta has to be a unit. Take R equals 1, alpha beta is a unit. Okay. So alpha is a unit, and that means A and B are associate. But this condition, we're going to, you would have to check it for all alpha and beta. It's tricky. But one way to ensure that all elements of this form lie in the Jacobson radical is to assume that all zero divisors belong to the Jacobson radical, because 1 minus alpha beta is a zero divisor, regardless of what alpha and beta are. So, final theorem, if R is a, again, commutative ring, and if the zero divisors of R lie in the Jacobson radical, then R is strongly associate.